Hello everyone, this is the continuation of the lecture on arrays. So, in this lecture we're discussing about vectors, matrices and n-dimensional arrays. The vectors we discussed in the previous video. Now we're going to talk about matrices and n-dimensional arrays. So as usual, please open the REPL such that you can replicate the examples that I'm showing in this presentation. Ctrl-Shift-P inside VS Code, Julia Start REPL, or simply open Julia from your applications. So let's go back to the example of the Mine Tower. And we are still looking for someone inside the tower. We are looking for Erika Mustermann. There are several floors, but now we will consider the fact that at each floor there will be several offices. So in order to reach Erika Mustermann, we now need two informations. We need a floor number and we need an office number. The floor number is going to be what we will call a row number, and the office number is going to be called a column number. So let's have a look at the map of our Mine Tower example. We still have a huge number of floors. I'm only depicting here from the 8th floor to the 12th floor. But now we have a second dimension. These are offices. This would be office 1, office 2, office 3. And if we go to the 10th floor, we notice that Erika Mustermann is actually living in the office number 2. So to reach Erika Mustermann, we need to go up to the 10th floor and then we need to go to the second office. So our 2D array is now a matrix, Mine Tower of floor 10, office 2 will be Erika Mustermann. That's where we find her. So this is the row index and this is the column index. That's how a matrix will look like. It's basically a table with elements inside. So we have a big matrix, big M here, and we have element numbers. So here it's a 2 by 3 matrix. That's the numbering of the different elements of the matrix M. And we will be able to access the elements of a matrix using the row and the column indices. So that's one way to define a matrix, and this we've used already in some of the examples. You can use the ones function to generate a matrix which is full of 1. So if you type this 1 of 2, 3, it will generate a matrix full of 1s, and the size will be 2 rows and 3 columns. So that's one way to generate a matrix with the same information everywhere. In the examples, we have also used the function zeros, which would populate this matrix with the value 0 everywhere. Another way to generate a matrix is to construct it by hand. So now we're going to generate this matrix, which contains 1, 2, 5 in the first row, and 8, 11, and 92 in the second. So to do this, we again use the square brackets. So you open a square bracket, you close the square bracket, and you enter line by line the element. So if you want 1, 2, 5 here, you type 1.0, 2.05, and once you want to jump to the next row, you use the semicolon. So when you put a semicolon there, it means we're going back to the next row, and then we can enter the other 3 components, 8, 11, and 92. So the operations, the mathematical operations we used before, they will also apply to matrices. And we discussed element-wise operations in the previous lecture. And that's an example of an element-wise addition. So we are adding m to m. So m plus m, and we will use the dot sign to indicate that this is a sum which is made element-wise. So of course we have the vector the matrix 1, 2, 5, 8, 11, 92, and if we add m to m, we will obtain this result 2, 4, 10, 16, 42, and 184. The element-wise multiplication will also apply to our matrix. So if we apply the multiplication instead of an addition, we will get the following result. Then another interesting element-wise operation would, for example, be the sinus. If you want to take the sinus of each element of the array independently, then notice the dot. The dot needs to be placed between the name of the function and the argument call here. This type of function broadcasting can apply to a lot of different functions. So we will use this. You will see dots hanging between the function name and the argument call in many of our examples. So when you do this, sinus is automatically applied to each of the entries of the 2D array here. Another example of element-wise operation would be the element-wise power, which we also used previously in our example. This is an element-wise power of matrix M. So point power 2, then each of the elements of the matrix are taken to the power 2. But if you do not want to make an element-wise operation, so if you want to make a matrix multiplication in the linear algebra sense, you will have restriction on the dimension, so it will be the same as in the case of vectors. A matrix multiplication may not work because you need to respect dimensionality of the product. So if you type m times m, you will get an error which is actually pretty clear. For once, you will receive an error dimension mismatch. However, if you try m multiplied by m transpose, then everything will work. So care needs to be taken because this operation, linear algebra operations, are not commutative. So you cannot multiply a matrix if the inner dimension is not equal to the number of columns of the left matrix. Remember this. This rule is very important. If you have a matrix of size m by n and you want to multiply it to another matrix, then the number of rows of the second matrix should be equal to the number of columns of the first matrix. So these are the row numbers and these are the column numbers. And the resulting product will have a size of M, comma, O, M, comma, O. So number of columns of left matrix should be equal to number of rows of right matrix. So n-dimensional arrays also exist. We are not restricted to 1D vector, 2D matrices, but you can also define arrays with a larger number of dimensions. This is an example of defining a 3D array. So here, ones of 2, 3, 3, we generate a table which will contain all these numbers. So you can use n-dimensional array. We are not restricted by this. And that's an example of a 4D array, for example. Luckily, in a lot of applications, we're often restricted by space. As in tectonics, we often consider 2D or 3D space. So most of the tables we deal with are on 2 or 3 dimensions. But in some other fields, things can be much more complex, like in petrology. If you do petrological modeling, you may need many more dimensions. So if you start working in doing thermodynamic computation, you may end up with a lot of dimensions, like FEO, MGO, and so on. Just to finish, I can show you some example of usage of 2D array. So that's a picture from a 2D simulation, of a tectonic simulation. And it looks like a drawing here, but in fact, it's the result of a computation and the visualization, the different colors you see here. These are representing a 2D array of composition. This is representing a color. So that's a heat map, as we did in the example, in which each color is a composition. On top of this, you see lines, and these lines are a contour of a 2D temperature field. So all the information to create this figure here is stored in 2 2D arrays, one for the color and one for the contour. In 3D, that's an example of a model, again, of fault network development. And to generate such a picture and to store the data here, we need a 3-dimensional array to store all the value of the visualized field here. So to summarize, arrays are very useful. They're used to store multiple values. So you can store 2D fields, 3D fields, or even more complex data. You can access the value and modify the value using indices. The element-wise operations are possible, but you have to be careful with the dot notation. And the rules of linear algebra apply to arrays. So one should also be careful when you multiply arrays. So the arrays can be 1 dimension, 2 dimension, and any, actually, number of dimensions. So that's it for this lecture. Thanks for your attention.